Hello, my name is Corbin Rivera. I'm an AI researcher at the Johns Hopkins Applied Physics Lab. And I'd like to thank the organizers of the Embodied AI workshop at CVPR 2021 for this invitation to speak about our submission to the iGibson Social Navigation Challenge. My teammates on this effort were Dr. Yijang Wang and Dr. Kapil Katyal, also from the Johns Hopkins Applied Physics Lab. We are part of the Intelligent Systems Center, and this work was done in collaboration with the Johns Hopkins Institute for Assured Autonomy. The iGibson Social Navigation Challenge had the goal of developing control policies to navigate a robot towards a goal position while avoiding the personal space of pedestrians. And today I'm going to tell you more about our approach. Our approach followed two paths. A learned approach that had the goal of implicit pedestrian avoidance and goal-seeking behavior, along with an additional approach that aimed to explicitly provide pedestrian avoidance and provide a force vector away from pedestrians. We combined these two vectors with a force addition model to result in our overall control policy. In general, this approach could be described as a learned policy with safety guardrails for the pedestrians. In more detail, our learned approach was trained via soft actor critic with a custom policy network. The policy network made use of a MobileNet version 2 network that was pre-trained and frozen based on the ImageNet dataset for embedding the RGB image input. The depth image was embedded using a convolutional neural network, and those embeddings were combined with the polar coordinates of the robot relative to the goal, and that resulting input was fed to separate networks to estimate the action value for our policy. We trained using 7 environments, leaving 1 for test. Our objective consisted of a penalty for personal space violations, which was just beyond what we knew that we would be tested at in the test environments. So we set it at 1.51. We trained the policy using a terminal reward of 10, attenuated by the number of steps it took to reach that goal. Our explicit pedestrian avoidance made use of YOLO version 3 for simultaneous classification of pedestrians and localization. The localization piece gave us bounding boxes for the pedestrians, which we then co-registered with the depth image and summarized to estimate the position of the pedestrian and angle relative to the robot. We could then use that information to generate a force vector away from the pedestrian. We persisted that force vector and decayed it over time so that even when the robot was no longer actively perceiving the pedestrian, there would still be a force vector away from the pedestrian. Our results, we obtained better than 90% success at reaching the goal for our in training environments. And we had the highest success rate in the challenge at 27% for reaching the goal in test environments. Overall, we placed 3rd, and we tied with the top submission for the success rated by time metric at 0.18. Our future work for this effort would be looking at how do we better generalize to test environments that we were not using for training. We noticed a drop in performance that we'd like to mitigate. With that, I'll wrap it up, and thank you for your time.